Okay, so we should be streaming now. Let me get me up there. I'm going to start with the screen share. So like I said, we're going to start today with a problem. Hold on, I got to hit a button here. All right, so I want to, whoops, we don't need that Zoom link there. So let's kind of remind ourselves about friction before we do circular motion, because a lot of the circular motion problems use friction. So page 99 in your workbook talks about friction. So remember, if two surfaces are in relative motion, we use mu kinetic times the normal force. Mu kinetic is the kinetic coefficient of friction. If two surfaces are not in relative motion, that's where things get confusing. If something in the problem indicates the situation is on the verge of slipping, we're going to use this formula, F equals mu static times the normal force. Some problems do not indicate that, okay? Friction is actually less than mu static times the normal force. So sometimes you're going to hear me say maximum possible frictional force. So this term right here, F equals mu static times the normal force, is actually the largest amount of friction that a surface and an object sitting on it can actually experience. So if you know the normal force and you know the static coefficient of friction, that gives you the largest possible frictional force. That doesn't necessarily mean that is the actual friction force. So let's do some friction problems and take a look at this one. All right. And then again, remember, friction points opposite the direction of relative motion or its tendency to move. All right. Okay. So in this case, problem 6.1 and 6.2 are really good problems for you to start with that have numbers. I think last time we alluded to 6.3 or 6.3 and a half. I'm not sure which. But I updated this problem. So take a look at your workbook. Turns out I had a typo in that problem statement. So read the problem statement put to 6.3 and a half, and you can update that problem statement. I accidentally asked about mass 2 minimum when I meant to ask about friction, or sorry, not friction, the zombie force F, or the applied force F. So update that, and then the solution will match that work. And I really apologize for that. That said, let's go to these problems we discussed. You could look at on your own. And let's take a look at 6.17. So this is a tricky one. And what I want to do is I want to draw some free body diagrams here and check these out. Now, if you have trouble following this one, just keep in mind you could check out 6.18 and a half later. All right, so let's set up 6.17 first. So yeah, what we most are concerned about is getting the FBDs right and writing the force equations correctly, and then the rest of the steps I expect you can follow at home. Okay. All right, so 6.17, we got a block here with some mass 2m. I'll share my whiteboard in a minute, just getting this down. We're going to apply a force horizontally. There's an angle theta. We know mu static equals 0.50. We know mu kinetic equals 0.30. And then this is problem 6.17. I'll label that too. Part A, F min to slide up. Part B, okay, got it all written down there. Hopefully you've had a second to look at it. All right. So this was my summary of the problem. We've got some blocks sitting on an incline here. We're going to apply a force. There's an angle, and we're trying to find the minimum force to cause these to slide up. All right. So when you see that wording, first, ding, 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 which force condition for friction applies for this problem?
Static.
Yes, we can actually say F equals mu static times the normal force. Okay. All right. So in this case, that's good. So let's draw an FBD of these. Now, what types of FBDs do you think we could draw here? Go ahead and unmute somebody random. Just tell me what you would maybe draw. You don't have to draw it. Just tell me what FBDs you might draw.
A system.
You could do a system in this case because we expect they're going to go together. What else? I guess each block separately. Let's not overthink it. So there's 3 possible FBDs we could draw here. M only, 2M only, and the system. Let's start by doing 2M here, then M, and then the system. Okay, so take a minute and draw those. All right. And I have a feeling we'll need a little bit more space for the 2M, so I'm going to scoot this over a little bit. 2M's probably got the most junk we got to think about. All right. I'll give you a second to draw what you think. Obviously, you've got the answers, so you could just look right now, but give it a shot first and then look at the answers. All right. I know there's a force F. I'll get that one in there. That's going to be on the system too. I'll raise it up in a minute. Lost a marker. What's the acceleration in this problem?
0.
0, because it's not actually sliding up. It says, what is the minimum force to cause it to slide up? The trick is, whoa, this marker is not going to work. Let me find another red. Oh my gosh, really? All right, maybe my kids took my red marker. Maybe there's one back in here. Oh, there it is. I put it in here. All right. There we go. Sorry about that. Whenever it's just on the verge of slipping, the trick is we set the acceleration to 0 and friction to these values. And that's actually just before it starts sliding, but that value will be approximately equal to the value when it actually begins to slide. Okay, so again, we set these 2 conditions because it's this. All right, so that means that's good. All right, and now let's maybe take a look at this. Make sure you check your masses here. 2M on the 2M FBD, M here, and 3M. And I'm missing some forces here. What's a force that I'm missing on 2M?
Friction.
Okay, and which way is friction?
It would be pointing down the ramp.
Down the ramp. Okay, if we're sliding up the ramp or about to slide up the ramp, obviously we're not sliding up the ramp, but we were told you're about to. So you're about to tend to move upwards. So whatever. All right, you got the idea. All right, how about on M? Is there also friction on M? I assume so. Now here we run into trouble. Just like with normal forces, we have different normal forces. We should probably have different frictional forces as well. So make sure you put a subscript on those. That's sloppy. Let's clean that up. F2, F1, and then here, we might just call this, just like before, for the system FBD, I don't bother to put a subscript on these two for the system FBD. These ones I do put subscripts on, and that makes sure this frictional force is different than these two. You could probably guess, once we do the work, this total frictional force will be the sum of both of those. Seems reasonable. Anything else, or are we done?
The internal forces.
What are the internal forces?
The normal force of 2 on 1 and vice versa.
Yeah, so let's start. You said on 1. Let's draw the normal force on 1. Which way does that point?
It would be pointing to the right.
Or
up the ramp, I mean.
Up the ramp, yeah. So we got to be careful because this is to the right and this is up the plane. So we do not want to the right. We want up the plane. Notice 1, 2, 3 vectors line up on the rotated coordinate system. So once the problems get nasty, using that rotated coordinate system is much better than saying straight up and down, right, left all the time. All right. So then let's call this, what would be a good name for this normal force? What subscripts do I generally use?
And 2 on 1.
Yeah, or 1, 2, or 2, 1, or something like that. All right, so let's go back over to here. What force am I missing on this one? Somebody else.
N1, 2.
That's
Going
right.
to down the plane.
Wait, shouldn't I call it N2, 1? What do you think about that question?
Same magnitude.
Yes, so we could say N2, 1, but because it's the same magnitude, I don't want to get confused later. Nice job. You said it correctly. Well done. All right, and these two are both supposed to be pointing the same way. All right, so in this case, we see the arrows are kind of all over the place. This one looks a little bit crappy here. Well, actually, from the front, you could see it. But so now we need to pick a coordinate system, and we should probably use the same coordinate system for all of them. And I argue it's just as easy to do this one. And let me erase this and put it somewhere else as any. So let me label this again. This was F, and this was mg. I think actually it was 2mg, right? Make that a little longer. The most common mistake here is people get lazy and do that. Don't do that. Remember, the components have to be parallel. And here you could guess you're probably going to get some standard mg cosine and mg sine stuff. Here, we're going to get some F cosine and F sine. We go over here to this one. Let me relabel it a little bit cleaner. This was mg. So similarly, we're going to split this one up on this coordinate system. Notice here the rotated coordinate system makes a ton of sense because now we only have to split up one vector instead of 3. All right, and then you get the idea. We can keep doing this all the way across. So splitting this one up. We see it's you got to split up 2 either way. So again, it seems reasonable. The middle one is the one that gets the most benefit. Okay. To be clear, in here, I'm going to put a purple dot by all the angles that are theta. So this purple dot, just so because it's difficult to squeeze that all in there, that purple dot represents theta. So this angle is theta, this angle is theta, etc. Okay. So that purple dot in there is theta. It probably looks black to you. It looks black on my screen. So whatever. And just in case, I'm going to get this even closer, lower this down just so you can get the maximum view there. Obviously, you've got the solutions as well. But I want to pause for a second. Any questions about that? Any questions? At this point, you could write down the force equations. That part, hopefully, you're getting pretty good at. But in this case, because A was equal to 0, remember, A was equal to 0, it doesn't really matter which way we call positive or negative, right? So you might as well call the direction it's moving positive. So I probably called this direction positive, and usually we call up or perpendicular to the plane positive. So this seems to match that convention. All right, and let me go in here. Let's take a look and see. Which problem was this? 6.17. Now, if you had trouble with that, come on now. Okay, there we go. Let's go to the solutions. There it is. So you can see this looks pretty similar to what we found there. I've got the equations. Notice the internal force was not present on there. These ones are actually drawn somewhat to scale, so that kind of gives you a feel for that. You might notice it is ridiculous to continuously draw all these force vectors to scale. If you're going to draw them to scale all the time, you first have to figure out all the forces completely, then go back and redraw the arrows. So from a practical standpoint, when you're doing these on a test or in the real world, usually you just draw these vectors. You might draw some of them slightly larger. Like notice here, this one was smaller than this one, was slightly smaller than that one. But doing much more than that, it gets very difficult to try and draw vectors to scale without doing the entire problem first. So don't freak out if you're like, man, how does he draw these to scale? I can't figure it out. It's because I use the answer to draw them. All right. So that said, great. Let's take a look at another question here. All right. Let's do another quick friction question just to kind of get you rolling. Unless there's questions about that, I figure you could read the rest of that at home and work it out at home. All right. Let's go to the next problem here. Yeah, and obviously you could figure out all this stuff once you get the equations. So let's go back to here. And there's the answers if you care, just in case. So that was what I found for the frictional force. And here's what I found for the normal force. So that you could do algebra at home. We don't want to waste class time on that. All right, so next. Ooh. All right, whatever. Let's go to 6.19 really quick. This is a good problem to kind of look at things. All right, 6.19. So I'm going to take a second to draw this up. You can have a second to read it, look on screen, whatever. I'm going to look at 6.19. And after that, we'll jump into circular motion, all right? This one's a little different. The zombie pushes with some force magnitude F. Those damn zombies pushing my blocks around. Starting from rest, the bottom block is pushed horizontally by a force of magnitude F. It accelerates to the right. Okay, we were told it accelerates to the right. I'm going to write that down right away, right? We're told mu static. That's the static coefficient of friction. We've got mu kinetic. Sounds like my neighbors are working on their yard out there. Apologies if you can hear that. All right. So 2 blocks are observed to move. Okay. We're told this piece of information. M1 does not slide. So I'm going to write that. That's a crucial piece of information. All right. Now, I think I've got most of it. Even though this isn't exactly the same, you can see I've got this kind of hard drive or something here. Old school, right? This is so old. Right now, flash drives are much more powerful than this. But basically, it's this situation where I'm pushing this one, and you could imagine I'm like my hand would be the table, right? So I'm pushing it this way, and there's another block on top, and it doesn't slide off. This is not outrageous. You're pushing the lower block, and the upper block comes along for the ride. Okay, totally reasonable scenario. Okay, here's what I drew just to kind of get us started. Again, we're looking at 6.19. So I'll race you. Try to get FBD. Let's do them in order, huh? How about we do FBD 1 on the left side, FBD 2 in the middle. And because they're not sliding, they're moving in unison, it is acceptable to do an FBD of the system. We cannot always do that, but here it is valid. So you don't have to do the FBDs in this order, but yeah. Why don't we start with the system FBD? Give me one force acting on the system FBD.
F.
F. Got it. Okay. Nice job. Somebody else, give me another one.
Friction to the left.
Okay. Was there friction down here on, was this the coefficients of friction on every surface or what? I'm going to read the problem. I just can't remember.
No.
Between all services.
Okay. So it said that was the frictional coefficient between all surfaces. Let's show everybody in the class where he's seeing that in the problem. So it says coefficients between all surfaces. So clearly there is friction between the bottom. Yep. Nice job. So what would be a good name for that? How about just lowercase f with no subscripts because this is the system? Well, I bet you anything there's a normal force too, right? I'll do that. And again, let's use this. And then there's probably weight, right? I'll call this M total G for right now. Sorry about that. Did I miss anything? I think that's it for this one. Obviously, there's some forces between blocks 1 and 2. We ignore those because they're internal. All right. And so just to kind of include this in here, let's get used to including the acceleration direction. All right. Let's go over here to which one do you want to try next? What do you think?
I would probably do FBD2.
Okay, so FBD2. Let's try it. I'll do the 2MG or M2G. I know that's down. Okay. Now what?
I would add the force F to the right.
Okay.
And that
Right.
thing experienced friction to the left, but it's the friction between the floor and the box.
Okay. So is that the same as this one?
Yeah.
So that's why I didn't bother to give it a subscript. Does that make sense?
Yes.
And so notice, normally here we might say F subscript 2, but I just want to point out that F subscript 2 is the same as the system. Similarly, how about the normal force? Normal force. So you could do this. You could either call them this or you could call them this in the system, FBD as well. So you basically, in this problem, we have to be a little bit careful. These two forces and these two forces should have the same labels because they are identical forces. So either put them both with the subscripts or both without. You call it. Okay. All right. Good. Is there anything else?
There's the friction between box 1 and box 2.
Okay. What
should-
is that point? And what is
so it
your
should go-
reasoning?
It should go to the left,
Okay.
and it's because the friction needs to be the thing that's pushing the box to the right on the FPD1.
Aha. So why don't we? So notice his reasoning requires us to understand FBD1. So let's come back to that in just a second. So somebody else, right? We'll come back to Esteban in a minute. Somebody tell me what is one force that acts on FBD1 on block 1?
The friction to the right to keep it on top of the block.
Exactly. So that basically is what Esteban was saying. If we don't have friction to the right, this block would sit still and this one would slide underneath it. Imagine if this was made out of ice. Okay, if it was made out of ice, or imagine if instead of having this thing sitting on here, there were wheels, right? It would sit still and this block would move out from underneath it. That means the book is moving this way relative to the drive, or said another way, the drive is moving backwards relative to the book. Friction on the book, or sorry, on the drive opposes the relative motion of the drive. So because the drive is tending to fall off the back, it needs friction forwards. And then going back to what Esteban said, by Newton's third law, that tells us this one. Sweet. Okay. So what's another force on FBD1?
Normal force between 2 on 1.
Yeah, and so here we probably don't want to use the same letter N because this is from the floor, this is from object 2. So why don't we just call this N21 or N12, whatever you want. Oh, and there's a question in the chat. My apologies. Oh, sorry, Isaac. I just saw that. My bad. Okay. So now let's see. Down, there's probably M1G, right? You know what I'm going to do? I'm going to color this one in purple. That way I could keep it straight from this other one, which is in green. Again, they probably all look the same color. The black and the purple look the same to you, but these two, right? All right, so are we done? I know this one's accelerating here. Go ahead, Esteban. Is that you? Oh, my bad.
Shouldn't there be a normal force on one on the box 2?
Yes, that's what I thought. Yeah, sorry, I thought when you unmuted, I assumed it was Esteban about to say that because I cut him off from finishing his FBD. Sorry about that. So there should be an N12 downwards on this one, right? Think about this. Whoops, let's make these the same, right? 1, 2, 2, 1 doesn't matter, but we just want to use the same. The idea is this. When you have these objects, the book exerts a normal force upwards on the on the drive. Therefore, by Newton's third law, the drive is exerting a normal force downwards on the book. A common misconception is people immediately ignore this force and just say, well, shit, shouldn't that just be M1G? Technically, that would be correct in terms of getting numbers, but it is not correct in terms of the name of the force. So you could get this particular problem right. And what happens is when things go at angles, people that replace this with M1G screw up and lose test points and have to retake my class. So please, please, please do not just write M1G down. Just because mathematically this is equivalent to M1G The force downwards is not M1G. M1G is a force that represents the weight of block 1, or the gravitational force that Earth exerts on 1. That has to be on 1. You can't draw M1G on 2. M1G is not a force. And what I do to screw with students is you could just take this whole thing and put it in an elevator, and then it's accelerating upwards. If this is accelerating upwards, you already know that normal forces and weights are no longer equivalent. Or if you put it at an angle, the normal force and the weight is not equivalent. The normal force is what's pushing down on 2. I don't know if you realize this, I'm harping on this because this is one of the most common mistakes students make. They get lazy and they say this is M1G, which is wrong. You might get lucky on this problem, but almost no others. All right. So at this point, I think we've got it all. Let's take a look at the solution or any questions. While you're thinking of your questions, I'll bring up the solutions here. So there we go. We see in this case, it looks like I did name them differently, F total and N total. But remember that F total and N total and N2 will be the same in this problem, right? So, all right, that's cool. Let's see here. All right, so there's something that we figured out. Okay, so you could get the answers. Great. Let's go back and read the questions. Let's see what we were supposed to answer. So we did this step. This is important. Let's read part B, everybody. Okay, so when I'm doing part B here, again, oh my gosh, why is this? If we do part B, which friction equation should I use? Should I use friction equals mu kinetic N? Or should I use friction equals mu static N?
Kinetic.
Okay, for which surface?
2 on the ground.
That's right. So down here, we would use F equals mu kinetic times the normal force. Excellent. All right. What about between the two blocks?
Static.
We would use
Are you-
friction is less than. We can't use equals anymore. This one is not applicable at all. Go ahead, whoever unmuted. What were you going to say?
I was going to say that. I was going to say the same thing.
Why is that the case? Why can't I use this lower equation? It's not moving. Shouldn't it be static?
Because it's not on the verge. If it was to tell
Right.
you it was on the verge, then you could use that.
Yeah. So it turns out the general way of writing it is static friction is less than or equal to. So you can use this equation. However, it's not really useful to us in a practical standpoint because we don't know what the value is. Is it supposed to be this or is it supposed to be less than that? We don't know. And so if you see this one, see the wording in part C, the maximum possible F, that's a clue that you could use F equals mu static N. So this is a great problem for working on kinetic, static friction, the two cases, because all three appear in this one problem. So make sure you go over 6.19 at home pretty well. All right. Sneaky. All right. And if you want to know if you really know your stuff, try this question. This one will get you. 6.21. This one gets people every year, and it's surprising. So 6.21 is a good one. All of these are pretty good here. This 6.24 is a good one. You might take a screenshot right now in case your wording has changed, some of the old books. 6.25 is a good concept question. So these are all referenced already, and this shows you how to make the graphs. We could talk about that more later. And I think we're about ready to go here to the next section. Oh, look at this one. That's a fun one. All right. So, oh yeah. And this is the other one I was looking for. I discovered this problem by accident. Well, by accident, by meaning I put it on a test one year and a lot of people missed it. So 6.33 is a good one to look at too. It's sneaky. All right. Oh gosh, look at this one. They're crazy. All right. So that, I think we're finally, oh my gosh. Sheesh. Ooh, 6.39 is good. Very good. Where are we at now? I'm looking. There we go. Circular motion. That's what I want to get to next. So page 111 is what we're going to next. So if you don't have any questions, you could start reading page 111. I'm going to pause for questions really quick. See if anybody has any questions before we go on. Any questions? You can do this stuff. All you have to do is practice. All right. So hopefully you like this a little bit more than projectiles. Most of the time people do. All right. So now, whoops. Oh, my kids. I had this all tied up. All right. What are we going to do? Let's do this instead. All right. So let me get some space here. We're going to start talking about objects moving in circular motion. So one example would be this situation. Right? And so when I have this thing spinning, you can see where this gets interesting is there's two different ways to describe circular motion. We could talk about the rate at which the angle is changing, but we could also talk about the velocity of any one point. So we could talk about the velocity of this little ball that's hanging here, right? So as this gets complicated, maybe I'll scoot, headphones, right? So obviously we could talk about the motion of one of these yellow balls that's spinning around, or we could talk about the motion of any one spot. Like you could say, let's describe the motion of this specific spot, the 70 centimeter mark of this meter stick, right? You could talk about which way it's moving. It has a velocity in the X and the Y, or we could talk about its velocity tangent to the circle and its velocity radially. And why is this useful? Well, look, this is not moving anywhere relative to this origin. It has zero velocity in the radial direction. It's not moving radially inward. It's not moving radially outward. And that simplifies things. And the tangential velocity, right? It turns out we could describe that as having constant tangential speed. And so this particular example where it's rotating at approximately uniform rate, right? Obviously there's a little bit of friction in that bearing there, but as this rotates, it's moving at approximately constant rotation rate. So the points on these, the individual points here are moving at constant speed. Now, if they're moving at constant speed, what do you think? Are they accelerating? So like I said, this point, like if we just look at the 30 centimeter mark or at this ball, assume I spin it, it's moving at approximately constant speed.
What I want to think is it's changing direction. So
You're absolutely right. The speed is not changing, but the direction of velocity. The velocity vector is not always this way. Sometimes it's this way, sometimes it's that way. And if we could, let's just look at this case down here at the bottom. Let's say it's rotating this direction. So it's rotating this way. Just before, it's moving slightly downwards. Just after, it's moving slightly upwards. The velocity changed from down to up. The acceleration direction is what? It was going this way, then it's going that way. Maybe a picture would help, huh? Go to your workbook. Not 0. Sorry, let me get the right page number. I think it's the next page. Go to page 112, I think. So this will motivate it. Oh, I did the top. So hopefully you can see this on the screen. Sorry, I did the top here. We'll go back and explain the definitions in a minute, but this is crazy. If I draw these two vectors here, This is V initial. All right. Now, I want to get delta V. Oops. If this is V initial, I want delta V, right? What is delta V by definition? Remind me. V what minus V what?
V final minus V initial.
Final minus initial. So if this is V initial, this vector right here would be negative V initial, right? It points the opposite way. So what would this look like? V final plus V initial, or plus negative V initial, excuse me, gives me delta V, right? The acceleration points the same direction towards the center of the circle. Isn't that crazy? It's moving with constant speed, but because the velocity changes direction, the acceleration is towards the middle. Isn't that crazy? Questions? All right. Let's go back and look at some of these definitions now on page 111.
What does
go
that?
ahead.
What does that mean when you say the acceleration is towards the middle? Like it's just like in a graph or something?
Let me show you something here. No, it points towards the center of the circle. Think about this. I got something for you. Here's this. This is going to be a little bit tricky with these headphones. I got to try and not do this. So here's me spinning this thing. Whoops. I'm not used to using my left hand here. Here, I'll do it like this. I'm spinning something, right? It's going in a circle. I'm trying not to hit. God, this is a small room when you're doing this. Okay. But so, geez, when I'm spinning this thing around, trying not to hit my headphone cable, what is keeping this thing from flying across the room? What object is keeping this from my hand attached to what? The string. Do strings push?
They pull.
They pull towards the fucking center. So don't fuck it up. Got it? Now I'm saying this because it's from 20 years of teaching the same thing, not you. All right. So this is what you got to be careful for. The strings can't push outwards. They pull towards the center, right? When you're driving and you turn a corner, you feel pushed to the outside. Why is that? It's because the car is pushing on you towards the middle of the turn, right? Car doors don't pull you. They push. So this is a very weird thing. Yeah, look at this. When you spin this thing, right, you can see it right here. These hooks are pulling the ball toward the center of the motion. If I whip it really quickly, I don't know if you could see that at all, but the idea here is, right, when this thing starts spinning, these are pulling it. Whoop, oh, man. Sorry. Yeah. So, right, there's a force towards the center. This makes sense. If there's a force towards the center, there's an acceleration towards the center. Crazy, right? Yeah, pretty wild. And this is probably one of the most difficult topics because you have this feeling from riding in a car, you feel pushed to the outside, but that's just not true. Remember that video I gave you of the marble going in a circle? Let me see if I could find it here. Hold on, I got it right here. Whoops. Oh, geez, whatever. There we go. Whatever. It's failing me. But I sent you a video last week of a marble moving around. The same idea, right? Without the tube. There we go. I think I got it now. Where's chat? I believe that was the marble in the tube video. It's the same thing. That one's analogous to you being in the car. If the tube is not there as the marble goes through it, right? When the tube is in place, it's pushing the marble towards the center. All right. But when the tube is not in place, the marble moves in a straight line. All right. All right. So now we need to get some notation here. So before we could do anything real, we need to start working on some notation. R hat. R hat means radially outwards. Theta hat means tangential direction, or a direction tangent to the circle. If you're in a math classes always choose counterclockwise as positive. This is a good convention. However, in physics classes, just like we sometimes call down the positive direction, in some problems, you may see me choose to make theta hat clockwise. That said, unless you have a good reason to choose otherwise, we usually assume counterclockwise is the positive direction, right? So now, if we want to describe these vectors, right, R hat means a vector with length 1. That's what the hat means. A unit vector means length 1, and it's pointing radially away. So that's what this is. Notice it's cosine in the I hat and sine in the J hat. So this is cosine theta, and this is sine theta. Think, how would you get the magnitude of that vector? If you were getting the magnitude of that vector, you'd square the components and add them, right? And so sine squared plus cosine squared equals 1. You take the square root, you get a size 1. Similarly, theta hat, this is a little bit different. You get a negative sine theta. So this is negative sine theta up here, or sine theta to the left. Normally, we don't write the minus sign. We just use the arrowhead. So the minus sign is right there, and this one would be cosine. Again, sine squared plus cosine is 1. Notice R hat dot R hat. What does that equal? Does anyone remember?
1.
1. Any unit vector dotted with itself is 1. What's R hat dot theta hat, if you had to guess? What's the angle look like between those?
90 degrees.
90 degrees. So the dot product is
0.
0. Okay.
yeah. So this is basically another coordinate system. Instead of using I hats and J hats, we're now going to start using R hats and theta hats. Okay. All right. So that's that. Don't overthink it. Now you're going to see me use CW for clockwise and CCW for counterclockwise. This T is going to be period. I'm trying to distinguish it from time, tension, torque, etc. Right? So if you just write capital little letter T, it could be confusing because capital letter T could mean string tension, right? V tan is tangential speed. Underline that word speed. Okay. A tangential, right? You could also call that A in the theta direction, relates to the change in speed. A sub R is going to be radial acceleration. Notice if you get a negative number for A sub R, that's an acceleration towards the center. AC and AR are used in different physics books all the time, and you have to be careful. To be clear, AC and AR both have the same magnitude. However, AR is radially outwards. You use a negative number for AR. So if I could, sometimes let's go up to this picture in your book here. Let's say this ball is accelerating. We would say AR, maybe at some point, AR might equal -3 meters per second squared. I'm making this number up. Don't wonder where it comes from. I'm just picking a random number. Whereas the same problem, somebody else might say A subscript C equals +3 meters per second squared. And so this is sort of one of those things like A sub Y versus G. AC is the magnitude of acceleration towards the center. Okay, so AC is the number and it's always positive. That happens to equal the speed squared divided by R. All right. So I'm going to pause there. Any questions on AC or AR? When you read books, this can be very confusing until you realize AC is like a magnitude and AR is the vector radially outwards. That's why this one gets the minus sign and this one doesn't. All right, let's keep going. This one is sneaky, super sneaky. Look carefully here. Look at this equation versus that equation. There's one subtle difference there. This one is taking the derivative of speed. It is not taking the derivative of velocity. So we see that speed and velocity, it's super critical that we are very clear in this chapter whether I say constant speed or constant velocity. Constant velocity means moving in a straight line. Constant speed could be moving in a straight line or could be moving in a circle, right? Or it could be moving in an ellipse, or it could be moving in some weird ass way. So we've got to be careful. Constant velocity is very different than constant speed. In all the previous problems we've done, that has not been an issue because we hadn't talked about circular motion yet. All right. Oh, man. Okay. And just watch out for that. So notice these two equations right here. So in this case versus this case, the AC, you have to put in a minus sign to make the direction explicit. Whereas here, AR contains the minus sign. It's implicit. All right. Okay. Let me see. Any questions? All right.
So
yeah, go
I
ahead.
have so in circular motion, the how should I explain it? The coordinates that we choose, it's the positive is always towards the outside of the.
It depends.
I'm just
So-
wondering because you said AR
Yes.
is always, so acceleration is always negative, so therefore the coordinate has to be going towards out.
I'll put it to you like this. In a strict mathematical sense, AR is always considered to be radially outwards. So let me get back my screen share here. So in a strict mathematical sense, if you're in a math class, you don't get to choose. These are always the directions of r hat and theta hat. Theta hat is always tangent to the circle in the counterclockwise direction. Similarly, r hat is always away from the center. However, in many physics problems, we flip both of those. Just like sometimes we switch X and Y to point upside down or left or right, we sometimes do the same thing. For example, let me give you an example. Like say this, oh, let me do, like this one. Yeah, well, how about 656? If I go in here, right? Let me see. Oh, let me find the next one. Sorry. Oh, here's one. So notice here was an example, 6.55. I didn't even draw a coordinate system, right? I just let my acceleration towards the center be my coordinate system. Or in this one, look at this one. Sometimes I use centripetal hat. So I put towards the center being the positive direction. And then this one I call, so we could see that in different problems, you might use different coordinate systems. Here's one where I called centripetal hat here and theta hat here. Here's another one where I used r hat and theta hat. So you can see there are many different correct ways to do problems. This is probably the best one to look at because you should get the same answer either way. So it sounds like you might want to put a star next to problem 6.52 so you can look at that. And that's usually one we do at some point. Yeah, pretty early on. So I will address those coordinate systems. Also, if you look at the table of contents, page 123 addresses this in your workbook. So if I could, I'm going to go to here and just pick page 123. So here is an example of how we do coordinate systems in the X direction, right? And there's how the results turn out. If you're curious of the equivalent, here's circular motion, and there's all the different choices you might choose. So if you're that kind of person that needs to understand this, I put it in the book. Otherwise, we can move on and address that after the whole chapter, which is kind of when I was hoping to do it. So it's there. If you need help with coordinate systems and understanding the different possible ways, there are several different good possibilities for this exact problem, right? This is the exact problem we started with. So does that get you going on that, Esteban?
Yeah, thank you.
Yeah, so it's worth reading, but I was going to hopefully gloss over that till the end of the chapter. So depends is the short answer. All right. Now let's see. Let me go back to here. Let's get back. I think we're on page 115 or so. Oops. I think we started on 111, right? So there we go. Page 111 again. All right. So I think we've kind of discussed this. Maybe we should actually do a problem. By the way, if you want, 6.48 and 6.49 discuss what happens if the speed is changing, and you could draw the acceleration vector. Okay. And when you do that, you'll see that there's components in different directions. Maybe this is a good time. You're probably bored here. This is a simulation you could use, right? So if I look at this thing and I have it moving in circular motion, we see right now the velocity is always tangent to the circle and the acceleration is towards the center in this case. What if we move in an ellipse? This is where things get tricky. Notice the acceleration vector doesn't always point exactly towards the center. Do you see that? So sometimes, like at the very right and the very top and the very left and the very bottom, the acceleration vector tends to point. But sometimes the velocity is speeding up and slowing down. Notice when the velocity is slowing down, there's a component of acceleration opposite the velocity. And when it's speeding up, there's a component of acceleration with the velocity. So what we're seeing here is at some random spot right here, we could split this acceleration. There's some perpendicular and there's some tangential. And we see that in this case, we would call this A subscript what? C or R? The way it's drawn, is that AC or AR?
I would say AC.
AC, towards the center, and this would be A tangential. So we could say in this particular instant in time, A tangential is opposite the velocity. You could say it's in the negative theta hat direction. And that's easier than trying to specify I hats and J hats. AC is operating towards the center. Towards the center is the negative R hat direction. Now, what's cool about this, if you watch this in circular motion and I play it, here it's going in a circle. Notice at any point in the circle, the acceleration is purely towards the center. So this is why if we have uniform circular motion, meaning circular motion with constant speed, constant radius, uniform circular motion, the acceleration tangential is 0. There's no acceleration opposite the velocity or with the velocity. All right. Now, if you want, this is what's really crazy. What I could do is I could just start moving this bug around in some weird path. I'm just picking some random thing with my mouse, right? And when you do this, as crazy as this seems, that is actually circular motion. It's circular motion where the direction and the radius and the speed and the acceleration are all changing all the time. What? Yeah, that's crazy. You could view the path on the screen right now as being a circle where the radius keeps changing and the direction that you're traveling along the circle keeps changing and the speed. So while this may seem insane right now, eventually the notation that we're using will help you understand any motion, no matter how weird it looks. It's crazy, right? All right. Let's do another question really quick. Let's do a concept here. I don't know if you could tell, this is a lot more exciting to me than some of the stuff we've been doing. In the immortal words of Samuel L. Jackson, no more blocks on the plane. Or maybe it was something else, I forget. Okay, so let's look at 651. I'm entertaining myself on page 113. Imagine you have a pendulum swinging back and forth. Okay, and it swings on a rope all the way. Okay, then it swings back. Okay. So imagine we're just doing the first swing from A to E. So as it's traveling from A to E, if it helps, here's what we're doing. Just that. Except we're just going to do one swing. So from A all the way over to B. All right. And so I want you to tell me what the velocity and acceleration should look like as it does this. As it swings from A all the way over to B. So to get back that question on screen, I'm going to give you, whoa, where is it? I'll give you a second to think about this. All right. So remember, a tangential is the one that's tangent to the motion. So try to figure out when it's going to be positive, when it's going to be negative, should it be zero, right? A centripetal, or AC, is towards the center. And to help you think about that, remember, we do have one equation. Well, we have two. We know that A tan is equal to dv with no arrow dt. It's the change in speed. And we know that AC equals v squared over r. All right. I'll give you 20 more seconds here. 30 more seconds. So we're going to take the break a little bit later today. If you're dying and you need to run out and take a break, you can do that at any time. Remember, you've got the live stream. You can come back. But so I was going to take the break right before the group activity at 1:35. So we got about 25 more minutes before we take our break. Okay, so hang in there. All right, let's take a look. And why don't we just go right to the simulation? Let's start over here. Initially, how fast is it moving? Not at all. So in this case, what's the acceleration towards the center at the initial point?
Should it be 0?
0. Is it going to remain at this speed, or will it change speed?
It'll be changing.
Yeah, will it go, will its tangential acceleration point parallel to its motion or against its motion? Will it point the way it wants to go or opposite that?
The way it wants to go.
Yeah, so there's the acceleration. As we run this, a half second later, it picks up some speed. At this point, AC has started to grow. However, the angle isn't so steep. A tangential is still pointing this way, but it's getting smaller. What do you predict will happen at the bottom of the motion?
A10 equals.
Yeah, because right at the bottom, the speed is not really changing that much, right? Because just before, if this helps, just before you were moving like this, just after you're moving like this, the angle is pretty negligible. This is almost the constant speed there, right? You're not changing much going up. So right at the very bottom, there's actually 0 A10. And then when we run this thing, we see at the very top, AC goes to 0. At the very bottom, AC goes, oh, whoops, sorry. I said that wrong. At the top, a centripetal goes to 0. At the bottom, a tangential goes to 0. And if you want, you could look at the answer in the workbook, and maybe we should do that to see if there's anything else I wanted to say. So let's go up one. So this is kind of what we're looking at if we could do it a little bit slowly. So notice at the very top, when there's no speed, you have no centripetal acceleration. And then the tangential acceleration is always pointing towards the bottom of the curve. All right. Tangent to the curve, but towards the bottom of it. All right. So that's just to kind of give you a feeling for which way these arrows point. At some point, we need to do better than that. We need to actually do calculations. So maybe we should do the next problem as well. All right. I hope you're getting excited by this. I hope this is slightly cool. All right. All right. So let's start. This is the one that I mentioned I would just a minute ago when Esteban was asking that question. Let's see if we can get some numbers for a practical device. Okay. So we're going to have a mass, and it's moving in a vertical circle. When I say vertical circle, right, I just want to be clear. This thing right now is not moving in a vertical circle. This would be moving in a vertical circle, like going up and down in a plane perpendicular to the ground. So, right, the vertical circle would be going up and around like this, whereas going around like this, that's different. That's, yeah, we'll worry about that later. Okay. So we're talking about vertical circle. You can think of it like this thing, spinning around like that. Okay. All right. So draw an FBD. All right. Well, I'm going to do the FBD in the solutions because I want to just talk about this thing. But I guess before we do that, what are the forces acting on this star? Right? It's tied to a string. What kind of force is that?
Tension
Tension. Which way does it point?
towards
Inwards.
the center.
Yeah, inwards towards the center. Good. Right? Strings don't push. Well, unless you freeze them and then with liquid nitrogen, then you could push with them. But that's not what we're doing. So there's a tension towards the center. What else do we have?
Gravity.
mg, straight down. And we see this is complicated. Already, it's this is ugly, right? Now, what about the normal force? Which way does the normal force point?
There's no normal force.
There isn't. Sometimes students draw this because they're so used to banked curves or banked planes, and this looks like it, but there isn't a normal force. It's not sitting on a table. So there's no inclined plane here. It looks similar. It's basically an inclined plane, except no normal force, right? A little bit like that. All right, so let's go in and look at the solution now. So here are the two styles on the right side of your screen that seem reasonable. One person might do the top style and use these coordinate systems, radially outwards and theta hat. If you're a mathematician, you would probably choose this. If you're going to code things in Python, you would probably choose this. However, in a great many problems, this is a very good alternative. All right. So these are two choices that should give the same answers for things like tension, right? It should give the same answers for the magnitude of A total. Obviously, we're not going to get the same signs on A total because one of these is outwards and one of them is inwards. But in general, you should get the same numbers for magnitudes. So I'm going to pause this for a second. Take a second to see if you agree with both of those styles and the force equation. So I want you to see if there's questions. I know how to do this. I need you to ask me questions if it doesn't make sense to you. So we're trying to understand that part. Look at the arrows. Take a second. I'm going to pause and let you digest this. This is intense. Whoops, that doesn't do any good. Let's walk through it. In the radial direction, this is negative, this is negative. That's why they're both negative. AC is the magnitude, and it points towards the center. So notice it's in the negative R hat. If we do the theta hat terms, or the tangential terms, right? This is negative. This is the tangential acceleration. That's also negative. So that's where these minus signs come from. Notice why I chose the lower coordinate system most of the time. Everything is negative, and I am such a positive person. You know that. Total lie, total lie. But yeah, sometimes it's easier to just do these lower coordinate systems because look, you don't get any minus signs. Generally speaking, minus signs can be annoying when you're working out problems because you forget them sometimes. So when we look in here, let's look at this one. In the theta hat direction, notice now this arrowhead matches, this arrowhead matches, so that's why they're both positive. Similarly, in the centripetal hat direction towards the center, this is now positive, positive, positive. That's why they're all positive. Now, when we solve for magnitudes, the results will get exactly the same, right? If you take this equation and multiply by -1, you get the bottom equations. We know these are the same. All right. Now, what I did was, I think, did I give you actual angles here? Look at this. In this problem, we know the mass, we know the radius, we know the angle, and we know the speed. Notice that speed, not velocity. So when I go back here, I just plug in the numbers and you get these answers. Watch out for this one down here. The total acceleration, I glossed this over this a little bit. The total acceleration, let me explain what that is again. Total acceleration is right here. I should probably, did I forget to write that on this page? Oh my gosh, I forgot to write it. So you should probably write this here, but this right down here is A total. So at the bottom of your page, that's the total acceleration, both components put together. I think that's somewhat obvious here, but I still should have said that's what I mean. When I say total acceleration, I mean add the two together. Okay, so let's go back to here. That's what I'm doing. I took this vector and I added it to that vector, and the magnitude is going to be this thing at this angle. Notice the angles don't match 30 degrees. Notice the angles are not 30 degrees. This problem right now is at a 30-degree angle from the horizontal. Whoops. Hold on. Let me get back to it. Sorry. This problem, the angle is shown as 30 degrees. When you do the math, the angle of the acceleration vector does not necessarily match that 30 degrees at all. So when you have these objects going around, and sometimes you could, yeah, so that's just something to know. I'm going to pause there. What do you think? Questions? This is pretty intense. I want to see if you guys have any questions. By the way, next week, we get to keep doing this more. So if you're thinking, shit, I'm never going to get this in one day, don't worry. We're doing another day on this next week, okay? Otherwise, you guys would be so lost. All right. Let's get back in there. It's so much. So you're not going to get it all today. All right. That said, maybe you'll get a couple of these concepts. Then next time, maybe you'll get a couple of the calculations and things. So, all right, this is a really good problem to do again at home without me there. All right, let's get to the next one. Uniform circular motion, right? So I'm just going to get both of these here. Now, if you're wondering what this is supposed to look like or how you get uniform circular motion, here's an example. Right? If you take this thing and you counterbalance it, so you have the same mass on this side and that side, we get a uniform circular motion. It's not perfect. Again, there's some friction, but it's moving at approximately constant speed, especially if I get it going here, right? Or you could imagine at an amusement park, you could use a motor to keep this thing going, right? And so you could use a motor or an engine to keep this thing turning at constant speed. It's totally realistic. So either you have these two masses equally balanced, or like in your car, right? The camshafts are going to spin at constant speed if you're driving, right? So you can get a uniform RPM rate, which begs the question, what are RPMs? Well, if you haven't used RPMs, maybe we should discuss those units. So uniform circular motion, that means circular motion with constant speed. The distance covered in one orbit is 2 pi r. The period, by definition, is the time to complete one orbit. Those of you that did oscillations for your talks tomorrow, the period was a time to complete one cycle, one orbit, same kind of thing, same exact term, period, time to complete one cycle. So what should be the period in terms of the speed and the radius? How do you get the period? The distance all the way around is 2 pi r. If we're moving with constant speed v, how do you get the period? Anybody?
I'm gonna take a guess.
Go
I
for
don't
it.
know.
It's okay to be wrong.
I'd say you probably have to divide v over 2 pi r or 2 pi r over v.
Okay, check the units. Which is it?
Okay, so
And while you're doing that,
meters-
I'm going to write distance equals rate times
meters per-
time.
So you got meters and then meters per second.
I'm going to let you go ahead and figure that out while you're on the right track. I think you're going to get it. So let me run it through this way. So you go ahead and think. The distance is 2 pi r. What's the rate at which you go around there? Somebody other than Esteban.
V.
V.
Yeah.
And then the time to get all the way around. And so, Esteban, does that match up with what you were thinking? What did you end up?
Yeah. So
yes.
2 pi r over v.
Exactly. So we got it. It's 2 pi r. And so the unit analysis is a good trick, right? If you're not sure, check the units. Omega. This is not W. W looks like this with pointy. Omega is this. This is omega. If you say W, I'm going to cringe and just say, you mean omega? A million frickin' times. So that's not a W. That's the Greek letter omega. It's the lowercase omega. This is weight. That's different. Omega is essentially your RPMs. We're going to call it angular frequency. Sometimes that's called angular speed. Standard units for omega are radians per second. We're going to learn, well, I guess we just learned, omega is 2 pi over the period. So now it turns out we can relate omega to V and R. Well, if you look at this equation. 2 pi over the period, that's going to be omega. So you just told me V, it's not your omega, it's our omega. So that means omega is V over R. This is interesting. Notice, I don't know, I'm going to pause for a second. This is how I remember it. V is not your omega, it's our omega. It's also written on your equation sheet. But here's the idea. Maybe you've seen this before. If I go to this example right here and try not to get myself caught up, right? And I'm going to lower this down a little bit. I'm going to look at this at the center. And what I want you to look at is towards the center of this thing, as it moves, you can almost make out the numbers. It's not that blurry. Whereas if you look out here, it's really blurry. Why? The speed of this part is proportional to its radius. V equals R omega, the rotation rate, the RPMs. And so look at this. Notice how blurry the numbers are on the outside, whereas you can almost read the ones that are in here close to the center. And so what we're seeing here is every spot on the rod has the same omega. Every spot has the same number of RPMs. Everything is rotating at the same rate, same omega. However, the speed is greater the farther you go out. As you increase your radius, points on the rod have more tangential speed. They have more V, but the same omega. Same omega, different V's. That's why you can read the text at the center of an old school record player, right? Because the velocity is small, even though it's moving at 33 1/3 RPMs. Oh my goodness. Okay, let's see. We still got 10 minutes before we take the break. All right. So this is a good problem to go through and make sure you have all these little facts down, and you could practice the unit conversions. Obviously, you could Google how to convert, and that's what you'll probably do on a practical level. However, radians and revolutions, I hope you know this. I hope you know that 2 pi radians equals 1 revolution. If not, I believe that's on the back of your book anyways, the back of your workbook. So you can look for all this stuff on the equation sheet. And you obviously know that there's 60 seconds in a minute. So this is revolutions per minute. And you could do all the calculations there. Here's an example. This is a good problem to do. It's supposed to relate to this one. That said, I want to jump on a little bit just so I make sure I help you as much as possible. We'll pick this one up next time. We'll pick this one up next time. We'll pick this one up in lab. Oh, this is a fun one. We'll do this next time. Cars going around curves. I tell you what we're going to do is this. We're at a good spot to stop because yeah, whatever. But I'm going to do more of these problems next week, and this is going to get really exciting. I do want to show you one problem here, a car on a banked curve. Now, this is obviously we're skipping a lot, so you're not going to understand a lot, but I want you to try to think about this one. So imagine you have a car. We're looking at a rear view of the car. This is a top view up here. We're looking at the car as you drive around on a circular track, but the track is banked at some angle theta down here. So the idea is the roadway is curved. Now, I'm not asking you to solve this problem. I'm asking you to draw an FBD. What do you think the forces are? Take a minute and draw them, okay? It's okay to be wrong. And we see There's negligible friction on the car because it's icy roadway. That might help. It's driving and it hits a patch of ice, so there's no friction. All right. Somebody other than Esteban. Esteban's been doing a great job today reporting in, and a couple of the others too. I know Don's been speaking up, and somebody else. I don't recognize your voice completely, but somebody new. What's one force acting on this car? Don't overthink it. Just tell me a force. You don't have to get the direction.
Normal force.
Normal force.
Perpendicular to the slope.
Okay, so we know there's a normal force this way. Good. And let's see what that was in the chat. MG. Right on, Isaac. Isaac, which way is MG? You can put it in the chat. I'm watching. Straight down. So we got these two forces. All right, good. That's it. That's the FBD. Piece of cake, right? However, which way is this car accelerating?
Towards the center.
What is towards the center? This way, right? It's not down the plane, Isaac, and that's what I wanted to warn you about. Think about this. You could imagine this car, here's the other side of the banked curve. Right? Here's the car over here. Do you agree this is the center? That's the most common mistake people make here. So that is towards the center. What force keeps the car from flying off the roadway in a straight line? Which force causes this thing to move in a circle?
MG.
No. Now, obviously, if there was no MG, this would be in outer space. So, okay, yes, it relates. Clearly, that's important. But which is the force that actually has a component towards the center?
The centripetal force?
What
The
is
normal
this?
force.
The normal force is the force. So this is the thing. People get used to saying the centripetal force. What is the centripetal force? Centripetal is a word that means center pointing. Now, centripetal force is a name for a real force that points towards the center. This component of the normal force is the centripetal force. So if you just say centripetal force, it's too vague to be useful, even though that is a true statement. So watch out for that. Centripetal force in this case is, what's this angle look like? Theta or 90 minus right here? What's this angle right here look like? Does it look like theta or 90 minus?
Theta.
Theta. Skinny angle trick still works. You could go through, right? So that's the normal force. So notice that N, what is it? Sine or cosine?
Sine.
N sine theta is the centripetal force. The horizontal component of the normal force causes this thing to go in a circle. If the curve wasn't banked, the car would go in a straight line right into the bushes and it would crash. Okay, so that is tricky. Now, I know it's time to take our break, but I'm going to show you what happens if we add in friction. Okay, there's a reason I'm showing you this. Hint, this problem may be useful in the group quiz in a minute. Well, let's take a look at it. Wait, which one was this here? So look at 6.6. I just want to show you this one in two different ways. So this is an issue that we are going to face possibly in your group assignment in about 12 minutes. The idea is sometimes in this problem, sometimes this style of splitting up the components perpendicular and parallel to the plane is very useful. However, because AC doesn't point parallel to the plane, we have to split up AC and MG, right? Whereas sometimes, as in style 2, we want to line up our coordinates this way, towards the center and in the z direction. And notice then we have to split up the normal force and the frictional forces. That's like the style I just showed you. And in different versions of different problems, sometimes the purple one is good. Sometimes the red one is good. For example, look at this equation right here. If you were trying to solve for F or the normal force, G, this style looks great because I could just solve for that term. Whereas over here, if I want to figure out AC, which relates to the speed, or maybe I want to figure out a mass or something like this, this one might be nice. So they both have advantages. And notice I mentioned this right here. So yeah, now why am I mentioning this? We are not doing circular motion on the quiz today. You're doing a free body diagram without friction. However, if it's on an inclined plane, sometimes you may want to split things up like this. Sometimes you may want to split things up like that. So just keep in mind, solution to 6.61, you could look at that if you need to split up your vectors in different directions. So at this point, what I'd like you to do is leave your Zoom on, take a 10-minute break. I'm going to make the breakout rooms while you guys take your break, and then we'll come back and we'll get into the group work. Okay? So I'm going to start doing that. You guys go ahead and take a break. If there's any questions first, I'll answer any questions you have first. Or if you want to just take a break. That was intense class there. All right. I'm going to get to work on these breakouts. Let me get this out of the way.